All right, welcome this afternoon. It is chilly and cool in Vermont today, and it sounds like warmer as we head farther south along the Appalachians. I'm Beverly Wemple and want to welcome those of you who are participating either to the meeting for the first time or back for those of you who've joined us before. It's my pleasure to introduce our speaker today, Dr. Katie Van Werkhoven from Research Triangle Institute in North Carolina. Katie is a senior research scientist at RTI with a diverse background in watershed and river systems modeling and analysis. Her work has included operational, academic, and consulting settings. She began her career helping US and international agencies to implement and improve flood forecasting systems, including 2 years building and operating a reservoir inflow forecast system for the government of South Africa. Following her work in South Africa, she worked in water quality management before returning to her roots, working at NOAA's National Water Center in Alabama to improve hydrologic forecasting across the country. As RTI's technical lead for the Cooperative Institute for Research to Operations in Hydrology, or CAIRO, Katie oversees several projects on forecast evaluation, and she has a new project moving forward for funding on improving flash flood forecasting in mountain settings, which is why we asked her to join us today for this roundtable. She also works with reservoir operators like Duke Energy, helping them to build and use forecast systems to guide their operations. Dr. Van Werkhoven has a PhD in civil engineering from Penn State University, a master's in hydrology and water resources from the University of Arizona, and a bachelor's degree in environmental engineering from Notre Dame. She lives in Boone, North Carolina, with her husband from South Africa, her 2 teenage sons, and her fluffy white mutt named Frosty. And with that, I will introduce Katie, turn it over to her for her presentation with thanks for being with us today.
Okay, well, while people are answering that, I will get my screen up and shared. Let's see. Hopefully that works. And go full screen. Look good. Can you all see my screen?
We can.
Okay. Okay. So thank you, Beverly, for the introduction. How do I minimize that? Did that go away on its own? Can you all see this top bar?
No, we're just seeing your slides.
Okay, good. Okay. So yeah, so as Beverly said, I have a long background working in the realm of flood forecasting. And being a resident of Boone in the Appalachian region, the experience of Hurricane Helene kind of solidified for me some motivation I have to continue to improve, find ways to improve flash flood forecasts in mountain settings. This is a photo from just a mile down the road from me. That was a house that was, swept off its foundation and washed down the river a bit. And what strikes me here is, I'm sure what you've all experienced in Vermont is like the simultaneous destruction and beauty in these regions. It was a beautiful time of year in the fall, and the destruction was evident all over the region, and it's so striking. I want to acknowledge my collaborators, Jason Regina and Jeff Zimmerman. As Beverly said, I work with the National Water Center very closely. There are 2 scientists there at the Water Center that have worked on this, some of this work with me. So I'm going to start with some general background in flood forecasting. What is flood forecasting? What's the state of flood forecasting in the US? And then get into the specific example of an evaluation of the forecast during Hurricane Helene. So the big picture, what I'm talking about when I say flood forecasting, and when you hear flood forecasting, maybe from the National Weather Service, what it is a translation of real-time observations and forecasts of precipitation, and that can be rain and or snow, into forecasts of hydrology. And that's river flow, it's water levels, total reservoir level, any variable of hydrology that's needed to make some decision about, something about the future conditions that is helpful for guiding decisions. I've focused here in the decisions being those related to flooding, Should authorities evacuate communities? Should they close roads? Where should they stage response equipment? But it also applies for reservoir operations and water supply. Any management function that is dependent upon water in some capacity may be users of hydrologic forecasts more generally, and flood forecasts are one subcategory of that. So more technically, what it looks like is from the very basic concept of flood forecasting is having data that represents past or observed rainfall conditions across a region. This is just representing it in as a time series here for one location. Past rainfall as well as a scenario of future rainfall, and that can be multiple scenarios. That rainfall is passed through a hydrologic model, and that results in a simulation of both past and future stream flow. Now that future stream flow can be used directly to make decisions, and stream flow itself is useful for decisions like reservoir operations. How much volume of stream flow is coming into a reservoir, is predicted to come into a reservoir, can help reservoir managers know how much to release in order to make enough space, right, for the flood wave that's about to come in upstream. That's one example. For something like flooding, what's really more useful for the decision-making process is inundation. Authorities need to know, have some sense of where the flood water is likely to go in order to close roads or evacuate communities. So that's one step further in the process. This is a very simplified view of the process, but just to kind of set the stage of what we're talking about. And a key point is that hydrologic forecasts, flood forecasts in particular, are highly uncertain. We all know that. We're familiar with weather forecasts being uncertain. With this top part up here, when you're given a forecast of rainfall of 5 to 7 inches, you know that that's a wide band and it may be plus or minus outside of that band. So what that translates to, if this yellow kind of represents the band, if you might think of a hurricane cone, right? That's the uncertainty cone. That same applies for quantitative estimates of how much rain might fall in a given location. And there's uncertainty around that, and that translates to an uncertainty band around an estimate of stream flow, future stream flow that widens as you move into the future. And that's very analogous to a hurricane cone widening as it goes further along its path, because it becomes more uncertain as you go further into the future. And models then add another layer of uncertainty. So this is representing the input uncertainty for flood forecasts. And then those inputs are passed through hydrologic models, and that adds another layer of uncertainty to the results. So there's multiple sources of uncertainty in a flood forecast. All data and models that are used in the process contribute to that uncertainty, and it is not possible to reduce it to zero. It's a reality of forecasting. There will always be uncertainty in forecasting due to randomness in nature. And then when we're talking about small mountainous catchments, mountainous watersheds, what I'm showing here, and uncertainty is particularly high and difficult to estimate. This is a very small watershed in Western Virginia. This is one example from a flood event in 2022. These images here on the left, these 9 images here, were different forecasts of where that bullseye of precipitation that was predicted. They knew that the atmosphere was very conducive to convective weather, but they didn't know exactly where the models did not know exactly where it was going to occur. So this is what you end up seeing in sequential cycles of forecasts is different potential scenarios of where very high rainfall might fall. And what's particularly notable here is this little watershed here never captured the bullseye of rainfall in any forecast never occurred on top of that little watershed. But that's where it ended up happening, was over that little watershed is where the bullseye of rainfall happened, and there was significant flood impacts over that location. So this spatial variability, particularly in small catchments, introduces a very high magnitude of uncertainty. And the response time of small watersheds also lends to challenges in flash flood forecasting in mountainous regions because of the steepness of the terrain combined with the size of small headwater catchments. You don't have a lot of time to respond, and those forecasts are highly uncertain because of the nature of the topography, the topographic influence on precipitation in the very small area over which you're trying to estimate the precipitation. So how do we handle uncertainty in forecasts? One option, which is the most common, is to ignore it. Essentially, in hydrologic forecasts in particular, the meteorological community is a little further along in characterizing uncertainty. But one option is to ignore it. It's simpler to produce and it's easier to use the forecasts. But it essentially leaves the monster in the closet. We don't know what that uncertainty looks like. We don't know what we're up against. We don't know how scary it might be. The other option is to quantify it. It's harder, but it leads to more informed decisions. And this is where the future is going, but we have some way to get there yet before it's commonplace in hydrologic forecasting. And what that does is tackles the monster in the closet. And at least you can see what he looks like. You can see how scary it is. It is difficult to make decisions when you have a very wide range of possible scenarios, but rather know what that wide range is, rather than ignore it and be wrong. Okay, that's kind of setting the stage for generally forecasting and the importance of uncertainty characterization. And now I'm going to give a very quick kind of overview of the state of flood forecasting in the US right now. And I added this little star to note that things are rapidly changing right now. So what I'm presenting is kind of the state of US forecasting today. But this might look different in a month or 2 months or 3 months. As we know, things are changing in the government right now. Forecasts over the last several decades, hydrologic forecasts have been generated by what's called river forecast centers. I imagine y'all are familiar with the Northeast River Forecast Center. You might work with them directly, or those of you in West Virginia and Pennsylvania, the Mid-Atlantic or the Ohio River Forecast Centers. There's 13 of them spread across the country, and they have about 4,000 forecast points. What that means is 4,000 points across the US where there's a gauge and where they issue forecasts. It sounds like a lot, but the density ends up being fairly spread apart in those forecasts. And this kind of gives a picture of that down in my area. This is Boone and Asheville, and you can see kind of what the density of forecast looks like. There's a fairly large area where there's no forecast provided by the River Forecast Center, and that's some of the motivation for some work that's been done over the last few years. And the river forecast centers do generate 5-day forecasts that are called deterministic, which means there's no uncertainty characterized there. And they also issue a 10-day forecast that does try to put those envelopes of uncertainty on the forecast. And that's more of a future direction. They're not all in operations yet, but that's the direction they're going. So they are trying to quantify that uncertainty at their roughly 4,000 points across the country. So in parallel to the river forecast centers over the last almost 10 years now, there's been an effort at the National Water Center to develop, it's developed several years ago. It has been in operations since 2016, what's called the National Water Model. And this is one of the motivations of the National Water Model. The biggest motivation was to fill in those gaps between the RFC forecast points. And what I'm circling here is those squares from the prior map here. Those squares are the river forecast points. And you can see in my region here, those dots are gauges, but they're not River Forecast Center forecast points. There's a gap where there is no forecast provided, and that happens to be right where Hurricane Helene hit, was over that region. And that's where the water model comes in to fill in those gaps. And it's been in operation since 2016. But it's not actively used for decision making. In some places it is, and it's getting there, but it's still under development. And this is just to try to demonstrate the National Water Model provides forecasts for 3.2 million locations in the country versus 4,000. Right now, it is an 18-hour or a 10-day forecast, and it does not include uncertainty estimation rigorously. There is an attempt to kind of coarsely estimate uncertainty, but that's also a future direction, and it's not quite there yet. So setting the stage here for that region where there was a gap, the water model provided the only source, the only source of forecasts in a large portion of the region that was impacted by Helene, and that's some of the motivation for the evaluation that I did. And then just lastly, noting kind of back to that first slide where it's difficult to make decisions based on a stream flow kind of graph, right? You need to know where the inundation is going to occur or where it might occur in order to make decisions like closing roads and evacuating communities. The Water Center is moving toward having generating and disseminating flood inundation maps is what FIM stands for. Flood inundation maps. There's currently about 30% of the country, that's the green and blue areas, the darker blue areas, have maps available when there's flood events occurring. And this is just an example of in Memphis, there's high flows still occurring from the flooding that happened 2 weeks ago in that region. And it's an example of what you can see if you go to the National Water Center Service website. Okay, so then that was a very, very quick overview, and I'm happy to take questions. I'm sure there are some about that toward the end, but I just want to finish off with kind of a summary of an evaluation that I did of the forecast performance specifically for Hurricane Helene. So to set the stage here, kind of thinking back to that other map, here's this region that was circled in that other map, the region where there are no River Forecast Center forecast points, kind of between Boone and Asheville in particular here. And that's where some of the highest areas of rainfall occurred. This is total precipitation for the Helene event. And you can see a lot of area of that hot pink, which was over 20 inches of rain in a 4-day period. Just incredible amounts of rain, as you all have heard much about, sure. This on the left is points where there's gauges, and the corresponding volume of in kind of per unit area volume of stream flow is the color, and the hatched circles here are where data were missing, where the gauges were either washed out or failed during the event. That's kind of setting the stage. So our first look at the forecast performance, what this map is here on the left is the mean total rainfall error. So very, very red means highly underestimated. Not enough rain was predicted in the 3 to 7 days prior to Helene. It was drastically underpredicted. Over here in this purple outline here is location by location on the y-axis. Every row is a gauge. And then along the x-axis is a forecast. So this is kind of sequential forecast cycles that were issued 4 times a day, what the error in peak flow was in each forecast, cycle over cycle at each location. Main story being it's a lot of red. So in the 3 to 7 days leading up to Helene, the rainfall and peak flow were significantly underestimated. They weren't seeing those 20-inch totals in the forecast yet up to 3 days prior to the event. Then when we got within that 3-day window, it started to show up. They started to have more, the forecast started to show much higher rainfall totals. Extreme rainfall and stream flow were predicted at some locations, especially right along that divide where blue means there was too much rain, red means not enough rain in the average of the forecast over that period. Right along that divide is where it actually was pretty accurate. It was getting those totals more accurately. In this box over here, you can see how the peak flow was too high, too low. It's kind of in different locations. Some places it was too high, some places it was too low, and even horizontally across, it was kind of varying between too high and too low in that 3-day period leading up to Helene. That's kind of a very broad look, hard to kind of digest what that means in a specific location. So now I'm going to kind of go through some specific locations and see what the forecast looked like and at what point in time was an extreme flow predicted prior to the event. So the main things to focus your eyes here are on these top 2 rainfall maps. The one on the right is observed. That's the radar, what actually happened. The one in the middle is a forecast for the same time period. So this is now 6 days prior to Helene. The rainfall forecast was too low. Now also focus your eyes down here on this kind of scatter of lines. The blue line is the stream flow forecast associated with this rainfall up here, that specific forecast. All the other lines are the full suite of forecasts that were issued throughout the event. So this was a low one. And what I'm trying to show here is as we step through time, how that changed. So you can see the next cycle, 5 days prior now, we start to see some rainfall, higher rainfall totals in the region. It's still not driving that stream flow up very high. It's still pretty low, too low. Then we go 3 days in advance and we start to see the timing improve of that hydrologic response here, but still way too low, and our rainfall is still not capturing that magnitude of 20 inches that occurred. And sorry, I didn't mention this dot and that little watershed is the corresponding stream flow here is for that stream flow at that dot, and its watershed is outlined there. And then 66 hours prior is the first forecast where it jumps up and it exceeds the 100-year flow, which is, it exceeded that at that location, although the black line, which is observed, we don't have data to confirm exactly how high the flow was, but we know it exceeded that 100-year flow at least. So at this location, 66 hours prior to Helene, there was a signal in the forecast that indicated extreme flow was going to occur at that location. And then the next step is then corresponding, tying that to an extreme flood inundation, the flood inundation that would occur based on that stream flow. Now I'm going to a different location, and I'm just going to step through a couple of other locations and note kind of the time, the amount of lead time that was provided at that location for extreme flows. So this is for the Swannanoa North Fork, a tributary to the Swannanoa River, was about 60 hours prior. The Watauga River up by me had an extreme flow forecasted 36 hours prior. It took longer for the forecast to show the extreme rainfall showing up in that further northern part of the region where I am. And then the Linville River was also about 36 hours prior, also in this more northern region. So those are kind of just some snapshots of what the forecast looked like prior to Helene. The main takeaways from that are in that circled area where there's no river forecast, the water model provided information to guide flood preparation and protective actions where there was no other source. The forecast indicated peaks of extreme magnitude between 24 and 72 hours prior to the peak impacts of Helene. So improvements are still needed. I didn't talk about uncertainty, right? In that evaluation, there's no uncertainty characterized in those forecasts. So that's kind of a question for discussion of how helpful the community thinks adding uncertainty and how to best make use of uncertainty in forecasts prior to an event like this. And then Beverly mentioned we're hoping to have the opportunity to work on a project to improve flash flood forecasts in the Appalachian region. Some of the questions we hope to tackle there are what's needed to help communities make best use of forecasts. Given small watersheds, high uncertainty, and short lead times, are there other tools that are more useful or more needed in these communities? And then are there other methods to increase the utility of forecasts with more lead time and better quantify uncertainty in these small watersheds? So that's what we're hoping to tackle. That was kind of a very quick run through some concepts here. And that's the end.
So our next roundtable, the 5th roundtable, is going to happen on May 15th, Thursday, May 15th, also at 2:30. And this is going to feature some of our work, Megan, who's on the call as well, about a project called Preparing Agents of Change for Tomorrow, which is a flood resilience planning and environmental literacy project that we have that is really geared at coupling the understanding of how rivers and watersheds and weather systems work, and working with youth to provide that foundational knowledge to then launch their participation in flood planning and flood response for their communities in Appalachia. And so if you're available for May 15th, we'll provide an overview of what the PACT project is doing. So thank you.
Thanks, Nico, and thanks to all of you for joining us today.